Welcome you all in this talk on compact metric spaces, and today we will see that the equivalence between sequentially compactness and compactness. We have already proved that a compact set is sequentially compact. So we will have to prove that the sequentially compact metric space is compact. So for that we have to define a concept of a Lebesgue number. So Lebesgue number is related to an open cover of a metric space X. So let F is a family G alpha, alpha is in lambda. Okay, let this be an open cover of a metric space X. Then a real valued lambda is greater than 0 is called Lebesgue number for the given open cover this if for each subset of X whose diameter is less than lambda is contained in at least one G alpha. That is, for every subset A whose diameter delta of A is less than lambda, then the A must be a subset of G alpha for or at least 1 alpha in lambda. Okay, so this way we define a Lebesgue number. So before proving that a sequentially compact metric space is compact, we will prove that in a sequentially compact metric space, every open cover has a Lebesgue number, and this result is known as Lebesgue covering lemma. So Lebesgue covering lemma says that in a sequentially compact metric space, every open cover has a Lebesgue number. So let us prove this one. So for this, let XD be a sequentially compact metric space and F the collection of open subsets of X. This is an open cover of X. Okay, then we will have to prove that it has a Lebesgue number. Suppose assume that F does not have any Lebesgue number. Okay, then from the definition of a Lebesgue number, for each natural number n, there exists a subset Bn of X such that the diameter of Bn, of course, must be greater than 0 and it is less than 1 over n. But this Bn does not lie inside Bn. So Bn is not contained in Gn. Bn is not contained in G alpha for all alpha is in lambda. Okay. Now for each n, choose a point xn in Bn. So this is Bn. So choose a point xn in Bn, and then we can construct a sequence xn of points of xn. Okay, and since xn is sequentially compact, so by the definition of the sequentially compact, every sequence has a convergent subsequence. So this sequence xn has a convergent subsequence xn k, and that converges to a point x in capital X. Now since capital X is small x is in capital X and F is an open cover of X. Okay, so this is an open cover of X. So the point X must lie in some open sphere, say G alpha naught. Okay, but G alpha naught is an open set containing X. Okay, so G alpha naught is an open set containing X. It means that X is an interior point of this. So this should be a center of some open sphere contained in it. So there exists an open sphere S epsilon x such that x is in the open sphere and open sphere contained in the open set G alpha naught. And now since x and k converges to x, by the definition of the convergence, there exists a positive integer n such that for all k is greater than or equal to n, we have dx and k x is less than epsilon y2. Now let us take n naught is greater than or equal to n be such that 1 over n naught is less than epsilon y2. Then from this inequality we can have that dx naught x is less than epsilon by 2, that is x and k lies in the open sphere with center at x and radius epsilon by 2 for all nk is greater than or equal to n naught. In particular, we can say that x n naught lies in the open sphere with center at x and radius half. Okay, and therefore, in view of this one, because here is the diameter of the open set Bn is less than 1 over n, we have the x n naught is in Bn naught and the diameter of Bn naught is greater than 0, but it is less than 1 over n naught from here. So it is less than 1 over n naught, but 1 over n naught is less than epsilon by 2. So this is less than epsilon by 2. And therefore, now since xn naught belongs to Bn naught as well as to as epsilon by 2x, and therefore B n naught and epsilon and the open sphere with center at x and radius epsilon by 2, the intersection of these two sets is non-empty. This implies that Bn naught will also intersect with S epsilon x. Now since the diameter of Bn naught is less than epsilon by 2 and Bn naught intersects with S epsilon x, we have Bn naught is the subset of S epsilon x and S epsilon x is the subset of G alpha naught. But this contradicts with the fact that Bn naught does not lie inside G alpha naught. That is to say, Bn naught is not contained in G alpha for all alpha, and hence F, which is the open cover of X, has a Lebesgue number. Now we are ready to prove our theorem, which says that every sequentially compact metric space is compact. Okay, so every sequentially compact metric space is compact. Sequentially compact means every sequence has a convergent subsequence. Compact means every open cover has a finite subcover. So let us take X be a sequentially compact metric space. Okay, and then we have proved that every sequentially compact metric space is totally bounded. So by theorem, this it is totally bounded. Totally bounded means it has an epsilon net. So then for a given epsilon positive, X has an epsilon net, say A. Okay, epsilon net A. Then A must be a finite set, x1, x2, xn. Okay, A consisting the elements x1, x2, xn finite. This is finite set, subset of X, and the X must be equal to the union of open spheres with center at this point and radius epsilon. So this X must be equal to this thing. Now we have to prove that X is compact. So compact means every open cover has a finite subcover. So we have to prove that every open cover has a finite subcover. So for that let us consider an open cover. So let F is equal to G alpha, alpha is in lambda, be an open cover of X. Okay, then we will have to prove that this has a finite subcover. So now, since X is sequentially compact by Lebesgue covering lemma, this open cover has a Lebesgue number by the previous theorem. Okay, say lambda. We put epsilon is equal to lambda by 3. Okay, so for each k runs from 1 to n, we have the diameter of the ball with center at xk and radius epsilon. Okay, so the diameter of this, because this is the ball, this is the open sphere with center at xk and radius epsilon. So the diameter of this should be less than 2 epsilon. But from here we are assuming that lambda epsilon is equal to lambda by 3. So this is equal to 2 lambda by 3, and 2 lambda by 3, this is less than lambda. So it means that the diameter of each open sphere, with center at xk and radius epsilon is less than epsilon by 2. Okay, and by the definition of a Lebesgue number, for each k we can find an open set G alpha k in F such that the ball, the open sphere with center at xk and radius epsilon, okay, lies in G alpha k. And this implies that the union of S epsilon xk, union of the balls with center xk and radius epsilon, okay, this lies inside the union of open sets G alpha k runs from 1 to n. Okay, it means, and this is what? This is, we have proved that this is equal to X. So it means that X lies in this union. So it means that X is equal to union of this one. It means what? It means that G alpha 1, G alpha 2, G alpha n, this is a finite subfamily of the open cover F. This is the finite subfamily of the open cover this. Okay, and so this open cover has a finite subcover of X, and hence X is compact. So this way we have proved that a sequentially compact metric space is compact. Now we have a corollary which says that a closed subspace of a complete metric space is compact if and only if it is totally bounded. So now finally we have the following relation. So if you have a compact set, then by theorem 4.3.5, it is the sequentially compactness implies the compactness, and compactness implies Bolzano-Weierstrass theorem by theorem 4.2.2, and we have proved in theorem 4.2.3 that sequentially compact and Bolzano-Weierstrass properties are equivalent. So sequentially compactness implies compactness, compactness implies Bolzano-Weierstrass property, Bolzano-Weierstrass property implies sequentially compactness, and therefore all these three concepts are equivalent. That is to say, in a metric space, okay, in a metric space, compactness, sequentially compactness and Bolzano-Weierstrass property are equivalent. Now, as I mentioned earlier, after each subsection, I have given several exercises. Some of them are given the proof or the solution, some with hint and some without hint or without proof. So you will have to try all these exercises by yourself first, and if you find difficulty to prove or to solve these exercises, and then you try to see the solution or the hint. First you do by yourself. So first exercise is that a compact subset of a metric space. So if A is a compact subset of a metric space X, then the drive set is also compact. Okay, so it is very simple, because we have already proved that the closer the closure, or you can say that the closed subset of a compact set is compact. We have already proved. Okay, so here is in some cases when you are solving the problem, you must see that in some cases we will have to prove logically, or sometimes we will have to use some results, and by using the result you can get the answer very easily. For example, here in this exercise we are proving A is a compact subset of a metric space X. Then we will have to prove that the drive set of A is compact. So drive set is what? Drive set of A is equal to A union the closure of A. Okay, and we have already proved that the closed subset of a compact set is compact. Okay, so by using this you can try to prove this one. So it is very simple, not very difficult. Now the next exercise says that which of the following statements, which are the following sets are compact. So for example, here we are taking the 0, 2 is subset of R. As you see, whenever you consider the R, in the R, a closed and bounded subset is compact. Okay, but in general metric space it is not true. So when you consider the R, just you check, just you see whether this set A is closed and bounded or not with respect to the metric, usual metric in R. So you see here is this set is not closed, but it is bounded. So it cannot be compact with respect to the usual metric on R. So this way you can think, the statement is very simple. Similarly, you can see here is the set A. Okay, so if you take the set A, this is your closed set, of course, and this is your closed subset. So A, this is your closed interval, this is your closed interval. Okay, and the finite union of closed set is closed, so this is closed, and of course this set A is bounded. So again it is closed and bounded, and therefore it is compact by Hein-Borel theorem, and so you can say that it is a compact subset of R. Now what about this one? Whether this is compact or not. Now you can see again, keep in mind whenever we are talking, we are looking for, or we are examining for a subset of a subset of Rn, then try to check whether the set is closed and bounded or not. Okay, for the others, so we will see other things, but as far as R is concerned, because we have the property that you are not supposed, we have the property that every closed and bounded subset of R is compact by Hein-Borel theorem. So we will use the Hein-Borel theorem to check whether a set is closed or bounded or not. So in all these exercises, here I B, C, D, E, I checked, but here is the solution is given, but for the rest you can do by yourself. So here, so especially up to here, up to E, we can see that whether you check whether these sets from A to E, they are, whether they are closed and bounded or not. Okay, even you can see that for the E, I have given this solution here, and I hope that you can try by yourself. It is very simple, not very difficult. Now, but the other exercise, which of the following sets are compact? So you take this set, okay, subset of R2, this is subset of R2, okay, and this is subset. Now here is we have let A, B be subsets of a metric space X such that A is closed and B is compact. Then A intersection B is compact. This you can treat as a result also. So that's why I am looking here is, so if A and B are subsets of a metric space X such that A is closed and B is compact, then the intersection of A and B is compact. Okay, so you can see that. So let G alpha be an open cover of A intersection B by sets open in X. Okay, and then we can take the G beta, which is equal to X complement of A. Okay, so complement of A we are assuming that is closed. So G beta is your open, and then G beta is open since A is closed. Let us denote by J is equal to the index set J is equal to the lambda index set union this beta. So we are considering this beta. So we claim that G alpha is in J, in this J is an open cover of B. Okay, so for that let B, small b is in capital B. Then either B is in this one if B is not in A, or B is in A intersection B, one which is a subset, because this is the open cover, so this lies in this union, and this implies that B belongs to G alpha for some alpha in lambda. In either case, B belongs to G alpha for some alpha in J, and therefore B is a subset of G union of G alpha lies in J, and so G alpha in J is an open cover of B, and because we are assuming that B is your compact set, so since B is compact, this open cover has a finite subcover, that is there exists a finite number L of J such that B is a subset of the union G alpha I, where alpha I is in L. Set B L beta is equal to L minus beta is a finite subset of J minus beta, which is equal to your lambda. Now we show that A intersection B is a subset of G alpha I, and alpha I lies in L beta. For this, suppose that B is an element of A intersection B, then B belongs to capital B, and which is the subset of this union, and so B lies in G alpha I for some alpha I is in L, but B in L A, so B cannot be in the complement of A, which is equal to G beta, and thus B is in G alpha I for some alpha I is in L beta, and thus the open cover of this has a finite subcover, namely this one. Hence, A intersection B is compact. So this is this exercise you can treat as a result, because it will be useful, and you will see that it is very useful in your further study, that a set is A is compact, A is closed, B is compact, then A intersection B is compact. Now, what can we say about the arbitrary intersection of compact set is compact? So here is we have the result, we have the exercises. So let A alpha be any family of compact sets of a metric space. Okay, then prove that the intersection is compact, while the union is not necessarily compact. So for this one, we can choose a fixed alpha naught in A and put A is equal to intersection of A alpha, where alpha is not equal to alpha naught, and take B is equal to A alpha naught. Okay, so here is what we are doing. We are taking one, because this is the intersection. So from here you can take one alpha naught outside. Okay, and the rest of the things are A. Okay, so and the which we are taking from the one A alpha naught outside, it is equal to your B. So B is your compact set, and this is what? This is your A alpha naught. This is your This is your closed compact set. So compact set means that they are closed. Okay, every compact set is closed, so they are closed, and arbitrary intersection of closed set is closed. So A is closed and B is compact, so the intersection of A and B is equal to the whole intersection. Okay, so then it is your compact by this exercise. So we can prove that this is your compact. Here is a little bit it is confusing. So here I am taking B is equal to B naught is this B, and A is equal to is this A. But here is this is not this one. So for the other way to prove that the arbitrary union of a compact set is not compact. So for that we will have to prove that we will have to give a counter example to show that arbitrary union of compact sets need not be compact. So for that, let us consider consider the sets an. Okay, so consider the set an is equal to the closed interval -1 and 1 for all positive integers n in the usual metric space R. Then each an is compact, because this we are considering an is a closed and bounded subset of R. So closed bounded subset of R is compact, so this is your compact set. So this is your compact. And now since it's but the union of this is equal to R. Okay, so if you take the union of this which is equal to R, okay, but the R, as we have seen, it is not compact. Okay, so this is not equal to, this is not compact. Now you can give several examples. Okay, so here are several other exercises. Give an example of a metric space other than R having Bolzano-Weierstrass property. Show that no finite subcollection of open interval this of S covers S. Show that the closed unit sphere S10 in the space L2, where the metric is defined in this way, in L2 is not compact. So there are several properties. The proof is already given here, so you can see the proof. And it's a very important thing. You can treat also as an example the real line R under the metric D star xy is equal to minimum of x minus y and 1. Okay, so the real line under this metric is bounded. Okay, but in general, okay, keep in mind the real line with respect to the usual metric is not bounded. So you can take this exercise as an example, as a counter example, where you can say that the real line with respect to the usual metric is unbounded, but with respect to this metric D star, which is defined in this way, is bounded. And you can also see that with respect to this the real line is bounded, but it is not totally bounded. So you can prove it very easily. But here is, you can also treat this as a exercise, as an example. And the real line R with the usual metric and Y is a subspace which is equal to, Y is equal to open interval 0, close interval 1 of R. Then prove that the open cover, okay, this is the open cover of this contains no finite subcover. Now finally you see here is I just when we are looking first exercise, we were looking about the closed and bounded subset of R. So we can see that if here is these are closed and bounded subsets of R. Okay, so just we need to show that whether the set A is closed and bounded subset of R, then by Bolzano-Weierstrass theorem they are compact. So no need to go to the definition of a compact set, that is every open cover has a finite subcover. Okay, just if you are checking whether a subset of R is compact or not, just you check whether it is closed or bounded or not. That is okay. Now what about the others? So you see, for the others, because here is these are the subsets. These are the subsets of R2 but not R. So here is for that to check. Here is we can see that we can use the proof that a subset A of the usual metric space Rn is compact if and only if it is closed and bounded. That is to say, if a subset A of the usual metric space Rn, not only R2, Rn is compact if and only if it is closed and bounded. So by using this exercise, and you can treat this exercise as a theorem, and so by using this theorem you can prove that you can also use this one to prove that these sets, whether these sets are closed and bounded subset of R2 or not. If they are closed and bounded subsets of R2, then they are compact. Okay, so you can mention that by Hand-Burrell theorem, in Rn the closed bounded subsets are compact, and because this set is closed and bounded and therefore it is compact. So just it is proved in one line. Or if it is given in the MCQ questions, say for example there are several questions are given this, and it is mentioned that which of the following sets are compact. So you have to check which sets are closed and bounded. Okay, so this exercise you can also treat as a theorem. Okay, so the proof is already given here, and here is to prove that you will have to use the theorem that let Ka be a compact subset of Rn, then by theorem this it is closed and bounded. But for the converse, here you have the converse. So for the converse, assume that A is closed and bounded. Okay, then fix epsilon is greater than 0 and set C tilde is equal to epsilon k1 upon n, epsilon k2 upon n, epsilon kn upon n, such that ki's are integers and I runs from 1 to n. And then we will see that C tilde is an epsilon net for Rn. And since A is bounded, okay, there exists a real number R is greater than 0 such that A lies in the open ball with center at origin and radius epsilon. Then the set C is equal to C tilde intersection this open ball with center at 0 and radius R is a finite epsilon net for A. So it is totally bounded, and by theorem this A is sequentially compact, and then by this A is compact. So this way we can prove. So usually in the exercises, whenever you have the exercises, we most of the time we use several results. Okay, all the exercises which are given, they are based on some results. So somewhere you will have to use results. So here you can see we have used several results. Now the next exercise is also very important, and you can use sometimes to prove that the set is compact. So let X be a compact set and Xn be a sequence in X, and then Xn converges to X. But we are not mentioning that this X lies in X. Okay, if this X is in X, then there is nothing to prove, because we have already proved that we don't know whether this is in X or not. So what we are taking, we are taking that the range set of the sequence and the limit point. Okay, the union of the limit point, that is to say the limit point union the range set, okay, of X, this forms a compact set. So we can see that to use that this is compact. So let this be an open cover of this set. Then there exists an open set G of F such that X is in G and Xn converges to X and G is open. So G is open. So there exists a positive integer n such that G contains all points of the set this for all n is greater than n. For each I runs from 1 to n, let Gi be an open set in F such that Xi in Gi. Then G union G1, G2, G capital N is finite subcover of the cover F, and hence this set is compact. So this way we can prove that the set is compact. Now another exercise which says that if A is a compact subset of a metric space X, then for any subset B of X, there exists a point X in A such that the distance between X and B is equal to the distance between A and B. Now here is the exercise is very important in the sense that it can, again you can see that you can treat this as a result. So A is your compact subset of a metric space. Okay, A is compact subset of a metric space. Then for any subset B of X, there exists a point X in A such that the distance between X and B, okay, is same as the distance between X and B is same as the distance between A and B. Okay, so here is the proof, and I leave this proof for yourself. And then we have if A is compact subset of a metric space and B is closed subset of X such that A intersection B is empty, then the distance between A and B must be strictly greater than 0. Now keep in mind A is compact and B is closed. So A is compact, B is closed, and they are disjoint. Then the intersection of the distance between them is greater than 0. Now can you provide any example where A is not necessarily compact, even then this is greater than 0, or this is not true if A is not compact, or if B is not closed, then this statement is not true? Can you provide some example? Okay, this is also an exercise for you, and it can be this, for example, this can be written as a MCQs. In several MCQs, it can be written as which of the following statement is holds. If A is compact, B is closed, and A intersection B is equal to empty, then the distance between A and B is greater than 0. Okay, or it is written like this: if the distance between A and B are two subsets of a metric space X such that they are disjoint, A intersection B is equal to empty, then the row AB is greater than 0 if the first one is A is compact and B is closed. Second, A is closed, B is compact. A is closed, B is closed. Third, A is open, A is compact, B is open. Fourth, none of the above. So which one is true? Okay, so the MCQs, you can see that they can be prepared, or they are from the exercises or from the results which we have already discussed. Now in a metric space, you can prove that X is complete if and only if every infinite totally bounded subset of X has a limit point. And also in a metric space, X is totally bounded if and only if every sequence in X has a Cauchy subsequence. And now here is the proof is given. So this is the end of the exercises and of the compact metric space. Okay, so now I stop this talk on metric spaces, and in the next talk we will discuss the continuity of a function defined between two metric spaces. Thank you very much.